Everyone, note 6.5 on modeling exponential growth and decay. This is going to be really important for this unit and when we get into personal finance, which is what we're going to be doing next unit. So it says the following relation is used to model exponential growth or decay. So our equation is going to be P equals I times our base to the power of T. Okay, so P is always going to stand for the current population or the current amount. Okay, so let me just zoom in on this a little bit so we can see this a little bit better. So P is the current amount. Okay, I is the initial amount, so it's what you started off with, which is exactly what we had before as well. It's always going to be the starting amount. Sorry about that. I don't know why this keeps showing up. So it's the initial amount. Okay, T is the time that it takes to grow or decay. Okay. B is called the growth rate, but it's only called the growth rate if B is greater than 1. But if B is between 0 and 1, this is called a decay rate. And just a reminder that growth means that it's increasing and decay means that it is decreasing. Okay, so let's go ahead and take a look at an example right here. So we need to talk about growth and decay rates right here. So if a population increases by 5%, so this means that this is growth. How can we display this as a growth rate? So here we're going to say that our growth percentage is always added to 1. Okay, so if it's 5% here, we would write 5% as a decimal, which is 0.05. Okay, so we're going to do right here 1 plus 0.05 is 1.05. So this right here is going to be the base. So we're going to use this as the base, and it's the growth rate. Okay, but for the next one, it says a population decreases. So this time, this is not growth, it's actually decay. So it's decay by 2.5%. So a decay percent is not added, it's actually subtracted from 1. So let's write 2.5% as a decimal. So 2.5% is 0.025. So we are going to do 1 minus 0.025. So we end up getting 0.975 if I were to type that into my calculator. So we're going to use this as the base here. And this right here represents the decay rate. Okay, so in example 1, we have an example of growth. So hoping to prevent extinction, 75 African bat-eared foxes were moved to an animal reserve in Africa. The fox population increased 15% each year over a 10-year period beginning 2007. Okay, so it says right here, write an exponential growth equation to model this relationship where P is the population and T is the number of years after 1997. Okay, so P stands for the current population, which is unknown. Okay, T stands for the number of years after 1990. Actually, this should say after 2007 because this is beginning in 2007 here. Okay, so we need to identify the other pieces of information here. So we need to identify what I is, and I stands for the initial amount. So we know that our initial amount right here is 75 because it starts in 75. Okay, so 75 foxes is our initial amount. B, to find B, it's increased, so it's growth, which means that it's added to 1. So to figure this out, I have to figure out what 15.8% is as a decimal. So I'm going to move the decimal place over 1 2 times, so I get 0.158. So it's 0.158, but I have to add 1 to it. So right here, it would be 1.158. Okay, so that's the B value. P is changing and T is changing, so I'm not going to fill in that information right here. So I'm just going to fill in what I do know. So I know that the I, the initial amount, is 75. I know the B is 1.158, and the T is constantly changing. Okay, so that's my answer for part A. Now, for part B, it says how many African bat-eared foxes were present after 5 years. So what this means here is that T is going to equal 5 because T stands for time, like we just saw right here. Okay, so I'm going to use this formula again. P equals 75 times 1.158 to the power of T, but instead of T, I'm going to use 5. So it's 1.158 to the power of 5. Now, all I have to do is go right into Desmos and type that in, and I'll get my answer for how many foxes we would expect after 5 years. Okay, so open up Desmos and type this in so you can see if you get the same answer as me. So I'm going to type in 75 bracket 1.158 all to the power of 5, and I get 156.172. But we don't want to say that there's 0.172 foxes, so we're going to round it. So we're going to say that this is approximately equal to 156 foxes. So we can say, therefore, after 5 years, there were 156 foxes. Okay, and then for question C, it's asking how many were present at the end of 10 years. So this time, my T value is going to be 10, so I'm going to use the same formula, but instead of 5 or T, I'm going to replace it with a 10 right here. So go right back into Desmos, and I can even just go ahead and delete this 5 and make it a 10, and I get 325, approximately 325. So we can say this is approximately 325. So we can say, therefore, after 10 years, there were 325 foxes. Okay, and that's how we look at exponential growth. Now we need to take a look at exponential decay. So this time, a cattle farm with a population of 240 cows is declining. So this time it's going down 3.4% each year. So we're going to write an exponential decay equation to model this relationship where P is the population and N is the number of years. So we're going to use N instead of T this time. Okay, so same thing, we're going to still use P equals I times B to the power of T, but instead of T, we're going to use N because it says N stands for the number of years. And I is always the initial amount. That's what we have written on top of our paper right here. So our initial amount is 240. Okay, now we need to find out what B is. So first thing I need to do is write 3.4% as a decimal. So I move the decimal place over twice, so I get 0.034. But because it is decay, it's subtracted from 1, okay, because it's being decreased by 3.4%. So when I subtract 0.034 from 1, I end up getting 0.966. So right here I get 0.966. So when I write my formula out, the I is 240 times 0.966 all to the power of N. And that's what my equation is going to be. Okay, so then it says what will be the expected cattle population after 5 years. So essentially this time N is going to be 5. So every time I see this equation right here, instead of N, I'm going to replace the N with a 5. So here I'm going to say P equals 240 times 0.966 all to the power of 5. So I'm going to go right into Desmos again, and I'm going to type that in. So I'm going to X out of this, and here I'm going to write 240 times 0.966 all to the power of 5, and I get about 202. Okay, so we can say right here that this is approximately 202. So we can say, therefore, after 5 years, there were 202 cows. And we are done with that question, okay? All right, so now the next thing that we're going to do is we're just going to look at specific types of exponential growth and specific types of a specific type of exponential growth and a specific type of exponential decay. So we have a little bit of a typo here where it says exponential growth. This should say exponential decay. Okay, so looking back at exponential growth right here, doubling is really a very common example of exponential that we will grow, or exponential growth that we will see. So doubling time is the time required for a quantity to double in size. When the base of an exponential function is 2, because you're multiplying by 2 every single time, the relation is described as a doubling. So an example of that would be if you have a population and like a population of rabbits, and it's doubling every certain amount of time because the rabbits are reproducing. Or you have a type of cell that's doubling every certain amount of time because the cells are multiplying. They're splitting up into from 1 cell into 2, and then the 2 cells split up into 4 cells, and then the 4 cells split up into 8 cells, so on and so forth. So if you take a look right here, it says P equals P sub 0 times 2 to the power of T over D. Now this formula looks very scary, but it's not bad at all if you take it little by little. So this is used to determine the population P after time T, where D right here is the doubling time. So how long it takes to double. And P sub 0 is the initial population. Anything you see that has a sub 0 is always the starting amount, just so that you know for future reference. Okay? So a bacterial culture began with 7,500 bacteria. So right here, I can say that P sub 0 is 7,500. Okay, its growth can be modeled by the formula n equals 7,500. So if you notice right here, P sub 0 is the 7,500, because remember P equals P sub 0 times 2 to the power of T over D, okay? Where n is the number of bacteria after T hours. So from the equation, we want to figure out what the doubling time is. So if you take a look right here, this exponent says T over 36. And remember, it's T over D, where D right here is the doubling time. So this number right here is our doubling time. So our doubling time is D always, and D equals 36, and it's in hours. So we know that every 36 hours, the bacteria is doubling. Okay, so we're going to say every 36 hours, the bacteria doubles. Okay, so then it says how many bacteria are present after 36 hours. So we're going to use the formula that they gave us. So the equation that they gave us is n equals 7,500 times 2 to the power of T over 36. But here we know that we want T to be 36. So we're going to say here, sorry about that, we're going to say here n equals 7,500 times 2 to the power of 36 over 36. Well, 36 divided by 36 is 1. So it's 7,500 times 2 to the power of 1. And we know 2 to the power of 1 is just simply 2. So I'm just going to multiply 7,500 by 2, and I get 15,000. Okay, which should make sense because after 36 hours it should double, and double 7,500 is 15,000. Okay, so we'll say right here, therefore, after 36 hours, the bacteria has doubled to 15,000. Okay. All right, so now question C says, how many bacteria are present after 72 hours, and how does this relate to the double period? So this time, our T value here is 72. So I'm going to replace the T right here with 72. So N equals 7,500 times 2 to the power of 72 over 36. Okay, but I know that 72 divided by 36, when I actually plug this into my calculator, is 2. So it's 2 to the power of 2. Then I'm going to follow BEDMAS. So I get 7,500 times 4. And when I do 7,500 times 4, I get 30,000. Okay, so we can say that this 30,000 right here is double this 15,000 that we got right here. And that should make sense because after 36 hours, it'll double once. And then after 72 hours, it'll double again. Okay, so that means that there are 2 doubling periods. Okay, so we can say right here, there are 2 doubling periods. In 72 hours, because 36 plus 36 is 72. Okay, so the bacteria would have doubled twice. And it's really important that we say that it doubled twice. Okay, so that's an example of exponential growth where we're doubling. Now we're going to talk about exponential decay, which is going to talk about half-lives. It's pretty much the same thing as doubling, except this time it's reducing to half the initial amount as opposed to being twice as much as the initial amount. So an example of that would be if you had some type of element and you want to know how old it is, every certain amount of time, it's going to decrease by half the amount that it was originally, okay? So right here, it says half-life is the time it takes for a quantity to reduce to half the initial size. When the base of an exponential relation is, instead of 2, this time it's going to be a half because it is half-life and not doubling, the relation is describing half-lives. Okay, so here m equals m sub 0 times 1/2 to the power of t over h. It's almost the same thing, except this time the base isn't 2, it's 1/2. So it's used to find the remaining mass, because this time it's decreasing, so it's what's left over, of a decaying substance after t time, where h right here is the half-life, like how long it takes. We're going to write time so we know it's how long it takes. And m sub 0, like we said, is always going to be the initial amount. So radon has a half-life that can be modeled by the equation m equals m sub 0 of 1/2 to the power of t over 25, where m is the mass of material in milligrams. So we want to know what the half-life of radon is. How long does it take for radon to decrease to half of its original size? Okay, so right here, our half-life, our time, is always the h value, and the h value right here is always this number right here, so it's 25. So we can say the half-life, so t over 25, shows that the half-life is 25. And we need to know what the unit is. It doesn't say in the problem what the unit is, but it should tell you that t is measured in days. Okay, so our half-life is 25 days. Okay, you're not expected to know what the unit is. It will be given to you in a problem. Okay, so part B says how much of a 4 milligram sample is left after 63 days. So right here, this is telling us that the 4 milligrams right here is our m sub 0. So we know m sub 0 is 4, and we know that our time is 63. So if our equation that's given to us right here says m equals m sub 0 of 1/2 to the power of t over 25, right here we can say m equals, our m sub 0 is 4, so we can replace this m sub 0 right here with a 4, times 1/2 to the power of t is the time that's gone by, so 63, and then we always divide that by however long the half-life is, which is 25 days. Okay, so all I have to do here now is I'm just going to go and I'm going to type this into Desmos. So I'm going to say 4 times, and then I'm going to write 1 over 2, okay, and then here I'm going to have to the power of, and then here I'm going to say 63 over 25, and make sure that whole thing is all inside of your exponent right here, okay? And we end up getting 0.697. So here we can say that this is approximately equal to 0.697. So we can say, therefore, after 63 days, only 0.697 milligrams is left of the 4 milligram sample. Okay, now if it's every 25 days right here, something that we should take into consideration is right here, it starts off with 4. After 25 days, it gets cut in half, so it'll be 2. After another 25 days, which is 50 days total, we're trying to get to 63, divide that by 2, we get 1. After another 25 days, which is 75 days, we get 0.5. So somewhere between 0.5 and 1 should be our answer, and 0.697 fits the answer that we're looking for right here. Okay, all right, and then our last question that we have here, it says, how long will it take a 400 milligram sample to decay to 25 milligrams? So this one's a little bit different. So here we know that the initial amount is 400 milligrams, okay? And we know that the new amount is going to be 25 milligrams. So this time what we want to do is we want to figure out how many half-lives So what we're going to do is we're going to start with 400, divide that by 2, and I get 200. Okay? Then, so that's 1 half-life. Okay? Now I'm going to do it again, because my goal is to get to 25. So I'm going to take 200 now and divide that by 2, and I get 100. Okay, that's my second half-life. So then here, my third half-life right here is going to be 100 this time, because that's how much is left now. 100, divide that by 2, and I get 50. Okay, our next one that we have here is going to be 50, divide that by 2, and we get 25. So we know it takes 4 half-lives. But that's not our final answer, because it's asking us to figure out how long. Well, we know a half-life is 25 days, okay? So each half-life is 25 days. So to get our final answer, what we need to do is we have to multiply 4 times 25, because there are 4 sets of 25 days. So our answer right here is going to be 100 days. And that's our final answer. Okay? And hopefully that should make sense to you. All right, that's it. Let me know if you have any questions, and I will talk to you later. Bye.